My name's Martin Lavelle, and I'm a theoretical physicist here at the University of Plymouth, and I teach calculus on the degrees and vector calculus in the second year of the degree. And what I want to do today, I want to talk to you about one of my favorite methods, which is called dimensional analysis. And I really do use it all the time. Mostly I use it to spot mistakes, but I also use it very much to understand the structure of equations, to make predictions, and also today we're going to prove a theorem. And that's a very unusual theorem inside dimensional analysis, but we'll come to that at the very end. So if you've got questions, please put them in the chat. Let me know, talk. Okay, so in a way, this talk is fulfilling an ambition of mine. I think it's the first time I've ever given a talk with a hummingbird in it. And this was in The Guardian the other day. I think it was Tuesday of this week. And it was talking about scientists who've understood how it is that hummingbirds, when they beat their wings, make a humming noise, in contrast to, say, mosquitoes, who, when they beat their wings, make a whining noise. And the reason I'm just mentioning it here is that if you look at the research paper, as I did, you will find that the word dimensional occurs 21 times in the research paper. So a lot of what they did in that paper was based upon dimensional analysis. Now, I'm not going to go through their paper today, but I'm just trying to indicate that this really is something that is very widely used. So let me start with a question, a very silly question. What is 1 kilogram plus 1 second? Answers in the chat, please. Yep, I agree, Alexa, I agree, Benjamin. It's not just the fact that they're different units, but there are different types of quantities. This is a silly question because it's meaningless. It's a question you can't ask. And this very basic idea lies at the heart of dimensional analysis. So you can only add, and subtraction is basically the same as addition, the same sort of terms. So you can add a length plus a length. So if you can see the camera, I've got a pen, I add another pen to it, and I've changed the length. So I can add lengths together, I can add times together. There is the time of this talk followed by the time for questions. That's a longer time. You can add two masses together, for example. But you can't add a length to a time. You can't add a mass to a length, for example. But you can multiply or divide, again, same sort of thing, different types of terms. And that's something I'm sure you're all very familiar with. So speed, for example, is distance over time, the distance traveled divided by the time taken. And if you think about that in terms of units, and I'm going to stop talking about units very soon, well, the units of distance are meters, the units of time are seconds. So it's meters per second, or as I will write in this talk, ms to the -1 meters per second. So this is this power notation, which I'm going to be using throughout the talk. So I hope everybody's completely happy with this, because it's the basic idea of the talk. You can't add or subtract different types of quantities, but you can multiply and divide different types of quantities. As long as you're happy with that, everything will be fine. Okay. So I'm not going to be using units. What I want to do is I want to talk about dimensions. So let's imagine X is a length. Well, there are lots of units for length. We've got meters, we've got miles, we've got parsecs in astronomy. So instead of saying we're going to use a particular type of length, Instead, let's just say that x has dimensions of length. X is a length. And you could have whatever set of units you want, but we're just going to generalize the idea. And the notation we use is we take our quantity, here it's x, we put square brackets around it, and that means what are the dimensions of the contents of the brackets. So this notation we're going to be using throughout the entirety of the talk. And if x is a length, the notation we're going to use is to say the dimensions of length are capital L. So if it was units, you might be saying meters or kilometers or whatever, but in terms of dimensions, it's just capital L for length. And this just means it's a length and it's completely irrespective of the units used. So whether you're in Europe and you're using meters, or perhaps you're working in America and you're using feet, then it doesn't matter. Your dimension is still capital L. I should point out a lot of America has gone metric. NASA has, for example, many years ago. To generalize this notation from lengths, the dimensions of time are time, capital T, and the dimensions of masses, mass, capital M. So we're going to be using capital letters for dimensions. Are people happy with this? Thank you, Benjamin. Okay. So what about the dimensions of speed? So all we're going to be doing is using the basic maths of powers of indices. So speed is distance over time. So what type of structure is this? The dimensions of speed are going to be the dimensions of distance over time. And we can just break it up into the dimensions of the quantity in the numerator divided by the dimensions of the quantity in the denominator. So this is distance, its dimensions are length. This is time, its dimensions are capital T. And that means L over T is LT to the minus 1. So that's the expression in dimensions. Were you to use units, that could be meters per second, for example. So my question for you is, what are the dimensions of acceleration? So what is acceleration? I hope several of you are already writing it down. Good, thank you, Luke, perfect. So acceleration is a change in speed divided by the time taken. So the dimensions of acceleration, well, speed, a change in speed is the same type of quantity as a speed. So its dimensions are LT to the minus 1. Time has dimensions of T. So this is LT to the minus 1 divided by T. It's LT to the minus 2. So that's exactly right. Okay. Now, the key statement next is that any quantity which has units has dimensions. So whether you're looking at density, at work, at pressure, whatever, these things have all got units, they've all got dimensions. And if I say that we have a quantity y, its dimensions, as long as we're only thinking about masses, lengths, and times, its dimension is going to be m for mass to some arbitrary power a, it's a constant, I don't know what it is, I don't know what y is, times L to some arbitrary power b, times t for time to some arbitrary power c. And then whatever this is physically fixes what a, b, and c are. Now, there are additional types of dimensions as well. You could be thinking about charges and so on. I'm not going to consider those things today. I'm just going to be thinking about masses, lengths, and times. We're going to get quite a long way just with them. So this is something we're going to come back to and use for predictions later, that any quantity, you can write its dimensions like that for some constants a, b, and c, which we can work out. The only things in science that don't have dimensions are so-called dimensionless ratios. And the dimensionless ratio is a ratio of two quantities with the same dimensions, and therefore it's just a number. So to keep the biological theme of the hummingbird, the example I've got here is your height, whatever it is, divided by the height of a giraffe. And that ratio is just a number. And this would be in terms of units, it would be some number of meters over some number of meters. It's just a number, presumably significantly less than 1. The dimensions of this are the dimensions of the numerator divided by the dimensions of the denominator. And the numerator is your height, that's the length, so it has dimensions of length. The denominator is the height of a giraffe, that's also a length, it has dimensions of length. And that is L to the naught, L to the 1 minus 1, which is 1. And you'll quite often see when people write down the dimensions of a dimensionless quantity, they write it as 1. And what they mean by that is 1 is L to the naught, M to the naught, T to the naught. It has no dimensions whatsoever. Okay, so this we will use later on, and this is an important thing to realize. Okay, any questions, put them in the chat. Now, we can use this to understand terms. So I've got here two expressions, one of which is the surface area of a sphere of radius r, one of which is the volume of a sphere of radius r. Which is which? Exactly, good. So the top one is the surface area, I'll just call it A, and that's because it has dimensions of length squared. The dimensions of R are length. 4 pi is just a number, it's a geometric number, it has no dimensions at all. So this is clearly an area because it's got length squared. And in the same way, this here is the volume because the dimensions of volume are length cubed, and any expression you ever see in your lives for a volume of a length multiplied by a length multiplied by a length. So it's, just thinking dimensionally. I know this is a simple example, but it can really help you to understand what's going on in equations in science and applied maths. So here's an expression for the area of a regular pentagon. And if I say that the perimeter of the pentagon is 5 times L, so this side here is L, that's L, etc., then you can work out that its area is this number times L squared. And again, the number is just a geometric number. You can work it out in terms of tangents. But this L squared is showing you that the dimensions work. Okay, so any expression for area is going to be a number times a length squared. Let's move on to another quantity and let's think about force. So Newton's law, F is ma, and let's think then what the dimensions of force are. So these two quantities are multiplying each other. So the dimensions of force are going to be the dimensions of mass times the dimensions of acceleration. So the dimensions of force are going to be m, capital M, for the dimensions of mass, and the dimensions of acceleration, you remember that? Dimensions of acceleration were Lt to the minus 2. So that is the dimensions of force. So any expression for force must have those dimensions. Now, let's think a little bit going from force to energy. So we can think about work. If you've got a simple constant force acting on an object and it moves the object through a distance in line with the force, distance d, then the work done by the force is F times d, force times distance. So the dimensions of work are going to be the dimensions of force times the dimensions of distance. So we can immediately write down that the dimensions of force are ml t to the minus 2. We just had that on this slide. Times d. D is a distance, so you know very simply what its length, what its dimensions are. I just said it, its length. So we now just do the simple tidying up. There's an L here and an L here. So when we multiply that together, we get that the dimensions of work are ml squared t to the minus 2. Now, this is the energy transferred by a force. So we make an important deduction from it. And our deduction is that any expression for energy must have this dimension. So the dimension of any energy must be ml squared t to the minus 2. So any expression which is going to have units in SI of joules has got to have dimensions of ml squared t to the minus 2. Does that make sense to people so far before I go on to the next slide? Thank you. Okay, so we've just said that work has dimensions of ml squared t to the minus 2. What other equations do you know for energy? Well, I'm assuming that you all know a half mv squared, and you also all know mgh for potential energy. So if I look at kinetic energy, the dimensions of that are going to be the dimensions of a half mv squared. Half is just a geometric number, forget it. So it's the dimensions of mass times the dimensions of v squared. I'm doing this very slowly. So this is the dimensions of mass times, now v squared means v times v. So its dimensions are going to be the dimensions of v times the dimensions of v. So it's the dimensions of v all squared. In other words, I can take this power and just pull it outside for the dimensions. So what we get is the dimensions of our expression for kinetic energy are m for the mass, and the dimensions of v is the speed. You remember what those dimensions were? So that's lt to the minus 1. When we square it, we square all of it. So we get this. So it's ml squared t to the minus 2, multiplying both of those powers by 2. And that's exactly what we got here. So I'm completely happy with that. So the expression for kinetic energy has the same dimensions as the expression we got for work, and any expression for energy must have it. So for example, I'm not going to be talking really about special relativity today, but you know, I'm certain, the famous equation E is mc squared. C in that equation is the speed of light. And it's not hard to convince yourselves that that's going to have the same dimensions as a half mv squared. After all, you don't have the half, but that's just a number. And you're replacing the speed v by the speed of light, c. So it's clearly going to have the same dimensions. That doesn't prove that E equals mc squared is correct, but it does prove or it would prove the similar way, if somebody claimed to you that E equals mc cubed was the right expression in special relativity, you could just say with dimensional analysis, no, that's wrong, because it does not have the same dimensions as any other expression for energy, so that cannot be an energy. So dimensional analysis is a very good way of seeing when something is wrong. And it's also a good way of recognizing in complicated equations, that bit there, that's an energy. Okay, so I have some exercises for you in this talk, and what I'm going to do is I'm going to send you next week, or Shauna will kindly send you next week, a link to a video giving you the answers to the exercises. I think, you know, the way you get benefit from a talk is actually by doing something, getting your fingers dirty. So you know the expression for potential energy, mgh, show it has the same dimensions. Must be true, or you would not be able to convert kinetic energy into potential energy, say. Okay, that's the first exercise. A good habit that I want to recommend to you is don't hide dimensions. So your weight, of course, on Earth, F is mg, your mass times the acceleration due to gravity. And you might be tempted to write F is 9.8 times, I've written G. That was silly of me, wasn't it? So I'll just delete the G. G is 9.8 meters per second squared times your mass, m. You might be tempted to write the weight like that, but that's really horrible. So this is nice. It makes the dimensions clear. It shows what the structures are. Here you've just got a number. So you're saying a force is just some mass. And of course you're not, because you're hiding dimensions in that number. So what I would like to say to you is that this is a good thing to write, and this is a bad thing to write, even without my mistake. And don't hide dimensions is a good thing. If you're going to put numbers into a calculation, put them in at the very, very end. Until then, keep symbols. Symbols show much more. Okay. Here are the famous constant acceleration equations. So things like S is ut plus a half at squared, v is u plus at, etc. And the question I want to ask you is, do these equations make sense dimensionally? And of course they do, otherwise they would be wrong. So let's just look at the first one. So if S is equal to ut plus a half at squared, it means we can add these two quantities, and that means they must be the same type of quantity. They must have the same dimensions. And this is equal to them. So again, it must have the same dimensions. So in terms of dimensions, this equation tells you that the dimensions of S are the dimensions of ut, which are also the dimensions of a half at squared. And this is really easy to verify, because the dimensions of S, well, S is just a length, so it's got dimension L. And ut has got dimensions, just think about it, LT to the minus 1 for u times t for this time here. So it's LT to the minus 1 times time. So L again. So LT to the minus 1t, and those factors cancel. So we just got L again. And here the half is a dimensionless geometric number. A has got dimensions LT to the minus 2, and t squared, well, that's got dimensions of t squared. And again, in the same way, t to the minus 2 and the t squared cancel. So all three of these terms have got dimensions of length. So again, we are happy. And again, this is not testing the half. It's not testing the plus sign. but it is testing the main structures and showing that they are the same sort of thing. Does that make sense to people? Thank you. Second exercise, the other two equations in the constant acceleration equations, v is u plus at, v squared is u squared plus 2as. Again, just check their dimensions work. And again, if they don't, those equations are wrong. But they're not wrong, the dimensions will work. Okay, let's think a little tiny bit now about calculus and how dimensions work in calculus. So to do that, I want to go back to the definition of a derivative. So the derivative gives you the slope of the tangent line to a function. And we can't just write that down so easily. So what we do is we define it through a limiting procedure. So what I've drawn here are our axes. This curve is y is some function of x. And here I'm saying is x, and over here is x plus h. This is the value of the function evaluated at x, and this is the value of the function evaluated at x plus h. And if I take the slope of the dotted line joining those 2 points, well, it's not the tangent line, but it doesn't look completely dissimilar. And I can get the slope of that line by saying, well, I'll look at the difference here, that function minus that function, that's the numerator here, divided by this distance here, which is x plus h minus x, and that's just h because the x's cancel. So that ratio is the slope of that dotted line. And then the idea is we say, well, we'll make h smaller and smaller. We'll bring this point in here and along here. And as we do that, we get a better and better approximation. And in the limit, a really important word in mathematics, as h goes to 0, this ratio is going to give you the slope of the tangent line. And this is our definition of a derivative from which all other ideas about differentiation follow. So let's think of functions of the derivative. Well, h is a change in x, so the dimensions of h are going to be the same as the dimensions of x. F of x is some function which is going to have dimensions, whatever they are. So we're going to get the dimensions of our function. And then we're just looking now at our definition. This is the change in the function's value. It must have the same dimension as the function. And the change in x must have the same, which is h, must have the same dimension as x. So it's this. So the moral of the story is the dimensions of the derivative are the dimensions of the function you're going to differentiate, and then you divide once by a power of the variable that you're differentiating with respect to. And that is going to tell you the dimensions of your answer if dimensions are relevant to the problem in hand. Okay, so let's look at an example of this. Does that make sense to people? Dimension of the derivative is the dimension of the function divided by 1 power of the dimensions of the variable. Okay, so let's look at an example. Let's assume for simplicity that x has got dimensions of length, and then the dimension of the derivative is the dimension of the function divided by the dimensions of x. So it's the dimension of the function divided by L. So if f of x is x squared, that would mean that the dimension of f of x would be the dimension of x squared, which is the dimension of x all squared. So that's L squared. So therefore, the dimension of the derivative just going back to here, is going to be L squared from the function divided by L. And L squared over L partly cancels, and we're left with L to the 1, or L. And that is, of course, true. So the derivative of x squared is 2x, and the dimensions of 2x, if x has dimensions of length, is just going to be the dimensions of x. 2 is a dimensionless number, and that's just L. So they agree, and we are happy. So if you think about differentiating x to the n, if x has got dimensions of length, you start off with a function of dimension length to the n, differentiate it once, and you remove 1 power of x. So you have x to the n minus 1. There's a number in front. Dimensional analysis does not tell you that, but it does tell you about the change in the power. You may say, well, hang on, maybe x isn't dimensionful, and maybe it isn't, but you can always assume it is. You can imagine it is, and then if it were to be dimensionful, what would the consequences be? So, you can think in an abstract way. Okay, so that's a little bit about differentiation and how dimensions work. Does that make sense to people? Thank you. What about integration? Well, let's, to be concrete, look at a definite integral. So you know how to define a definite integral, a la Riemann. You look at your function, draw its curve, and then you say, I'm going to integrate, say, from A to B. And you take this area, I'm drawing a positive function, so I can think of it as an area. You break it into lots of little rectangles, and then you say the definite integral is the sum of, if the function is positive, the area of these rectangles. If the function is negative, it's minus the area. So it's the value of the function times delta xi, this step here. And we add all of these things together. And in the limit, as the number of rectangles approaches infinity, this sum is going to give you the integral. This is our definition of a definite integral. Now, each of the terms in the sum has to have the same dimension. That's clear. So in the sum, each of them is going to have the dimensions of the function, whatever that is, times the dimensions of this step in the variable. So what we're going to have is the dimension of the function times the dimension of the variable. This is expressed through the measure here in our notation for an integral, and it corresponds to the step widths. And this is the integrand, and here you see it corresponds to the height of this rectangle, or if it's negative, minus the height. Okay, so the key idea that we have is the dimensions of an integral are the dimensions of the integrand multiplied by the dimensions of the measure. So let's look at an example. Let's assume again that x is a length. And if you want to integrate x cubed with respect to x, well, the dimensions of that are going to be x cubed from the integrand, dimensions of x cubed, which are L cubed, times from the measure, the dimension of x, which is L. So x cubed times x is x to the fourth, dimensions L to the fourth. And indeed, of course, you all know that the integral of x cubed with respect to x is x to the fourth over 4 plus some integration constant. So again, dimensional analysis does not tell you about the 4, but it does tell you about the x to the 4 or the dimensions. And this is something which, when you're looking at more sophisticated integrals, can still be very relevant and helpful for you to understand structures. Okay, does that make sense to people? Okay, thank you. So I haven't got time at the moment to go through a proof of this or an argument for it, but it's worth emphasizing that apart from structures with simple powers, something which is, say, a length squared or a length cubed divided by a mass squared or the square root of a time, apart from things like that, everything else must be dimensionless. So in particular, trigonometric functions and their arguments have to be dimensionless. Exponentials have to be dimensionless. Logarithms, dimensionless. So if you meet, for example, this lovely Gaussian function, e to the minus ax squared, this must be dimensionless. It's an exponential. Its argument has got to be dimensionless. So the dimensions of ax squared, forget the minus sign, that doesn't have dimensions. It's got to be dimensionless, so it's 1, using the notation we used earlier. So dimensions of a, and again, we have a limited number of letters, so a here does not mean acceleration, it's just something in this expression. But the dimensions of a times the dimensions of x squared have got to be 1, dimensionless. So the dimensions of a are 1 over the dimensions of x squared. So 1 over the dimensions of x all squared. So if x were to be a length, the dimensions of a would be 1 over length squared. So it would be the reciprocal of an area. And you need that combination to make the argument of any exponential function dimensionless. And that's an important thing. It really helps you a great deal to understand things. So, for example, if you're seeing something like, something is the sine of omega t, know that that combination omega t has got to be dimensionless. Okay. Let's make a prediction. So the prediction I want to make is about a pendulum. So here's a very contemporary pendulum. It's a mask. So if I let it oscillate, what happens is it has a period to go through a full oscillation. And that period can depend upon the length of the pendulum. It could depend upon the mass at the end of the pendulum. And of course, it would be different if you were on Earth with the acceleration due to gravity that's around us now, or if you were, say, on the moon with a much smaller acceleration due to gravity. So we have these 3 variables: mass, length of pendulum, and acceleration due to gravity. What we want to think about is how will the period of the pendulum, which is a time, I'm going to call it by the letter tau. I don't want to call it capital T because in this talk, I'm using that exclusively for the dimension of time. So how does this period tau depend upon M, L, and G? And you can immediately see that what they could depend upon arbitrary powers. So let me say that this is M to the A, L to the B, and G to the C. And there could be some number. I have no idea what the number is. And I think you're starting to see dimensional analysis normally does not tell you what the number is. I'll just put a hashtag in front of it. I don't know what the number is, and I'm not going to get it today with you. So how does the period of our pendulum depend upon these quantities? Now, you might think it could also depend upon things like the density of air and so on, but I'm ignoring air resistance. So normally in mathematical modeling, there are always quantities that we ignore, and that's one I'll ignore today. So that's all I can basically imagine that this could depend upon. So let's make that calculation. So we have said that tau is going to be some number that we don't know what it is, times the mass at the end of the pendulum to the power a, the length of the pendulum to the power b, and the acceleration due to gravity on our planet to the power c. I hope I've got them in the same order, mlg, yep, that's right. So let's just see what the dimensions are, how the dimensions agree. And by thinking about the dimensions, we're going to turn this into a set of simultaneous equations and solve for A, B, and C. So we'll take the dimensions of tau, and it's going to have to be equal to the dimensions of whatever our expression is. Now, we can break this up into products of the dimensions of the number, but that is just a number, it doesn't have any, times the dimensions of mass to the a, times the dimensions of the length of the pendulum to the power b, times the dimensions of the acceleration due to gravity, that will go in a moment, to the power c. So we know what the dimensions of mass are. It's m, capital M, dimensions of length, capital L, and acceleration was, you remember, Lt to the minus 2, all to the c. So the first thing to know, and on this side, on the left-hand side, this is capital T because the period is a time. So this equation written here is actually 3 equations. What it's telling us is that the powers of these dimensions have got to match. Now, t is t to the 1, that's what it means. And it's also, if you think about it, m to the 0 times t to the 1 and L to the 0 times t to the 1. So expressing this as equations, we get the following. M to the 0 is m to the a. So a is 0. And that's our first prediction. It's something you can do easily at home. Make yourself a little pendulum with a piece of string, tie a mass to it, estimate its period. You could let it go through a few oscillations and time it with the stopwatch that's built into your mobile phone. And then you could attach a heavier weight at the bottom, but without changing the length, and do the same experiment, and you will find that the period is unchanged. So the period does not depend upon the mass. And you can start to understand that if you try to turn this into a differential equation, but I'm not going to do that now. What about lengths? Well, we have length to the 0 on this side. So on the other side, we have length to the power of b, and now we multiply out this bracket, we get L to the c. So it's, sorry, that should not be a t. You just get times L to the c. So that tells us that b plus c, which is the power of L here, is 0. So that's a useful equation immediately. And then we have t to the 1 on this side, and on this side we have t to the minus 2c. So therefore, c is going to be minus 1/2. Minus 2c is 1, so c is minus 1/2. b plus c is 0, so b is plus 1/2. So just by thinking about it, we have come to the following conclusion. The period of our pendulum is going to be some number, 2 pi, times And then it's the length of the pendulum to the half, that's the square root of the length of the pendulum, times the reciprocal, negative power, of the square root of the acceleration due to gravity. So that's L over G. And that's an expression that it's easy for you to look at and just check through and see that the dimensions do indeed work. That's length, that's LT to the minus 2. Lengths cancel. You've got t to the 2 in the root, so it gives you t to the 1. Dimensions are perfect. Okay, so that's a prediction. And I think things like that are really quite beautiful. You can also go on further. I decided in the end I wanted to do it, didn't have time. You can go on and do things like Kepler's third law in exactly this way. If you say that you've got Newton's law of gravity, so you have a one over distance squared law of gravity, Kepler's third law basically drops out. But I have got an exercise for you, which is the range of a projectile. So if you just fire a projectile at some speed v at an angle theta to the horizontal, angles are dimensionless. We're not going to say anything about the angle. It's going to come down and hit the ground at some distance r, which we'll call the range. And what I would like you to show is through dimensional arguments, just as we were doing here, show that the range is some number times v squared over g. Now you can set this up as a differential equation, you can integrate it, solve it, you can find out what that number is, but just by thinking a little bit as we did, you're able to work out this key factor that the range goes as the square of the speed divided by the acceleration due to gravity. And this number will, of course, depend on the angle. Okay, so that's another exercise for you to do, and I will give you the answer to that next week. But let's finish the talk, if I may, with a theorem. It's a maths talk, we want a theorem. So I want to just show you how dimensional analysis can be used to prove Pythagoras's theorem. Nothing you say to do with mechanics, but I have seen people using dimensional arguments to do problems in economics as well. So it is more widely used. So we're going to draw a right angle triangle, sides A, B, and C, which is the hypotenuse. The angles are right angle, theta, and then this is 90 minus theta, so that the angles add up to 180 degrees, or pi. So the area of anything is always going to be a length multiplied by a length. And the length that I'm going to choose to characterize this right angle triangle is its hypotenuse. So I'm going to say the area of the triangle is some number, which will of course depend upon the angle theta. And once you fix theta, this angle changes with it. So there's going to be some number, but times c squared. And that is our dimensional start for proving Pythagoras's theorem. Now, some of you may be thinking, well, hang on, why do you not say that the area is some number, whatever it is, times a times b, or should we be adding these things? But remember, a over c is the cosine of theta, so a is c cos theta, and b is c sine theta. So excuse me, so some number times ab is going to be some number times functions of the angle times c squared. So any combination of a, b, and c, which could give you an area, can be expressed in terms of dimensionless quantities that depend on the angle in the triangle and the product of the hypotenuse with itself, the hypotenuse squared. As soon as you believe that, everything is going to be really, really easy. So what I'm saying is the area of a triangle is the hypotenuse squared times some number which depends upon the angle theta. We can work out what that is, but I'm not going to worry about it. So here's our triangle. We can make it larger, changing the area and changing the hypotenuse. We can make it smaller, whatever we want to do. What I'm doing here, though, is I've dropped a perpendicular here, and that means that I've broken my triangle into two triangles, both right angle triangles, and I'm going to say that this has got area A1 and this has got area A2. So the total area of our triangle is A1 plus A2. And the area of our overall triangle, remember we said that was some number, times the hypotenuse squared. So what can we say about A1 and A2? Well, you look at A1 and the angle here is theta, and that means that the angle here is going to be 90 minus theta. And you look at this triangle, that area is 90 minus theta, so it must be the case that this angle is theta. And indeed, you see these two angles add up together to give you 90 degrees, the right angle. So we see that by dropping this perpendicular, we've actually broken our right angle triangle into two copies of the triangle, one with hypotenuse A here, and one with hypotenuse B. So the area of A1 is going to be whatever the number is for this angle theta times A squared, and A2 is whatever the number is times B squared. So we see that whatever the number is times C squared, it is the number times A squared plus the number times B squared. Those numbers cancel because they are the same for every term. And this is really unusual, by the way. It's the only case in dimensional analysis that I know where the unknown constants cancel. If you ever find another one, let me know. I don't know of any. So just cancelling those things tells us that a squared plus b squared is c squared, and that's Pythagoras' theorem, which we have proven. So dimensional analysis gives us predictions and it gives us a proof of a theorem here. So I've basically finished, and there's lots more one could say. I genuinely think this is a really useful technique. It helps you spot errors. So if you're doing a long algebraic calculation, it might be dozens of pages long, and you've got a term that says that a volume of a cylinder, say, is pi rh, that's wrong. There's no discussion. That is just definitely wrong, because that has dimensions of length squared, volumes have got dimensions of length cubed. I've tried to indicate how you can make predictions, and I've given you an exercise to look at to make a prediction. You can understand structures in equations much better this way, and we've proven a theorem. There is also, I just thought I'd give you a link. I'll give you a link to it as well in the email next week. But there is a very well-known story about somebody being able, from a film, to predict the size of the first nuclear explosion. And if you put "how big was the bomb" and "that's maths," one word, into Google, you will get a story about that. But we have to draw an end at some stage, so I'm going to stop here. Are there any questions at all? Thank you for listening and for comments in the chat.